All right, this is the recorded lecture for Wednesday, February 18th. It'll be our third lecture on dynamic programming, and we're going to get into some problems that are close to my heart and that I like a lot. Since it's a video lecture, I think I'm going to go a little bit faster than I normally would because I trust you to pause the video whenever you feel like it and experience the lecture at your own pace. So, for starters, our stumper. So this here is our friend, Professor Patty Larceny. She's trying to steal books from the Claremont College's library. Um, every book has both a weight and a monetary value. She's trying to get the greatest possible total monetary value while staying within a 15 kilogram weight limit. That is, she can only put at most 15 kilograms of books in her backpack. So if you want to think about this, pause the video. In a couple of seconds, I will jump forward and show off the answer. All right, if I've done my math correct, these 5 books should be the optimal solution. So it looks like we've got two, um, 2, 3, 10, 20, $22 in total value. And if we add up the kilograms, that'll be 1, 2, 8, 12, 14 kilograms, meaning we haven't actually used the entire weight limit, but we've achieved $22 in value. And you can imagine how, if there were many, many books to look through, this might be a pretty tough algorithmic problem. So if you want, think about how we might go about solving it. Um, it's not much of a spoiler to say that we're going to solve it using dynamic programming, but there are other reasonable solutions, including both heuristic solutions and rounding solutions and greedy solutions that are, in some sense, cool ways to approach this problem. All right, dynamic programming part 3, some related problems, that is adding numbers together, and at the end we'll talk about reductions between problems. This is an XKCD comic. Covering one of the problems we'll talk about today. As a reminder, homework 3, that's the first dynamic programming homework, is due tomorrow on Thursday if you're watching this on Wednesday. I will be out of office at a conference Wednesday, Thursday, and Friday of this week. So if you want, you're welcome to use my Calendly link to set up a Zoom. If you've got an urgent question, send me an email, but I won't otherwise have my normal office hours. There will be normal Goodring hours, so Wednesday night, Thursday night, Friday during the day, all of the other times you would normally be able to get to your Grooters. But if you're running into difficulties this week, shoot me an email, let me know. I will try to be responsive. Last time we talked about edit distance. So edit distance is a problem that captures the distance between two strings. So 2 lectures ago, we saw another way to do this. That was the longest common subsequence. Edit distance is a little bit more general. In particular, we say if we are allowed to change a string by inserting a character, deleting a character, or substituting a character, we want to find the minimum number of changes that allow us to turn one input string into another input string. And if they are similar to each other, it'll be a small number of changes. If they're very different from each other, it'll be a large number of changes. And that's a decent proxy for how similar are these two strings. The way we solve this problem is essentially we guessed the operation by which the last character of one string was turned into the last character of the other string, and we worked backwards. And this was pseudocode of the function we came up with, the recursive function, not the dynamic programming function. The reason I've blacked out the name of the function is because I want to emphasize that once we know a recursive solution for our problem, once we've written down pseudocode like this to let us solve the problem, we can create a DP solution without having any other knowledge about what the problem is or how it works. With just the information that's currently on this slide, you could build a 2-dimensional DP table to solve this problem. So for starters, you probably want to know the dimension of your DP table. You can get that by looking at the input, and in particular by saying, all right, first input is this string, and we'll look at a prefix of this string of up to n characters. So n, I think for the way we've written this function, runs from -1 up through n, which means it can take n plus 2 different values. Similarly for m. And that tells you, okay, we're going to need a dynamic programming table that stores the value of this function call for all possible pairs of n plus 2 values for the first parameter and m plus 2 values for the second parameter. If we want to fill in this table, the first thing we need to do is figure out what our base cases are. That is, which function calls we can compute without having to do any recursion. And our base cases are given to us by this part of the function that's highlighted. So it's telling us that if one of the two strings is empty, essentially we have to insert or delete characters to create the other string. That's the fastest edit distance transformation between them. But we don't actually need to know that to say, oh, these are base cases. This tells me how to fill in the -1 row and the -1 column in my DP table. So I start there. The next step is to figure out how you fill in each cell of the DP table, which is given to us by the actual recursion. So looking at these calls, this tells me if I want to fill in this orange square, which we'll say has the coordinates nm, I might need to look at the cell n-1, m-1, that is above and to the left, or I might need to look at the cell n, m-1 to the left, or m, n-1 directly above. And that holds for any cell in my table. I might need to use the cells immediately above or above and to the left. That tells me how to fill in the cells, and it also tells me that as table filling order that is always increasing always increasing to the right and downwards is going to be a safe order to fill in my table because I'll always have the reference cells that I need. So with just this black box, if we've written the recursive function, we can write our dynamic program. I want to do a little tangent before we get started with solving the knapsack problem. And this tangent is talking about how we measure the runtime of algorithms in terms of their input size. So at this point, we've been casually using asymptotic, that is big O notation, for a while. And hopefully we know that the reason we're doing this, the big picture, the reason we're measuring the runtime of algorithms in terms of their input size is because for any algorithmic problem, or at least for the vast majority, we expect slower runtimes for larger inputs, right? If you want to sort an array, the bigger your array is, the longer your algorithm is going to take. So our runtime is a function of n, and n has got to be a parameter that captures how big the input is. Formally, this is what it means for a function to be polynomial with respect to n. It means that n is some parameter, which formally we can define as the number of bits it takes to write down the problem instance. And n is the parameter going to infinity, and then b is some constant. So this would be functions like square root n, or n squared, or n to the 1, which is linear time. All of those are polynomial functions. And as computer scientists, we know that we can basically take any data object and write it as a binary string and count the number of bits we need to write that object down, if it's encoded efficiently, as a great proxy for how big that object is. So this turns out to be a definition that applies very generally to just about any input. So what that means is that polynomial is defined with respect to n, the number of bits it takes to write down the problem input. And at this point, you might be saying, well, duh, what else could we use to measure the input? There's a lot of other characteristics of problems, and they might show up in the runtime, especially if they affect how our algorithm works. So if our runtime was something like, let's say, big O of n squared times some other parameter p, part of that expression is polynomial in n, but there's also a part of that expression that doesn't necessarily depend on the input size. So the runtime of our algorithm might scale in a way that's not totally dependent only on the input. We'll come back to what that means for us later when we design an algorithm that'll have another parameter involved in the runtime. But as some examples of how we've done this in the past, we can say things like an S character string uses big O of S bits, at least as long as we have a finite alphabet. So if I've got some finite number of characters, I'm going to need a constant number of characters to, um, sorry, if I have some constant number of characters, I'll need a constant number of bits to encode each character. So I'll need big O of S bits for an S character string. Um, Integers are an interesting case. I think we briefly mentioned the other day that um, the integer c uses actually about log of c bits to write down. And this is a fancy way of saying for a number like a million, the number itself is really big. It's a million. But the number of decimal places I'm using to write it down, which is how much space I'd be using if I wrote it down inside a computer, is just these 7 decimal places. And if I wrote it in binary, I would need something like 20 binary bits. So the amount of space it takes to write down an integer is proportional to the log of the size of the integer. Um, we might even have a slightly more complicated problem like interval scheduling, where maybe we encode an integer as, or an interval as 2 integers, a start time and an end time, and we might even have an input that's like a little bit bigger than k for k intervals, because perhaps for every interval, we need something like log k bits to write down those start time and end time numbers. Um, Fortunately, in this case, even if we're writing runtimes as like big O of k squared, um, well, this is still polynomial with respect to k log k, because log k grows a lot more slowly than k. Uh, but it's a subtlety that we should keep an eye out for. So I'll pause there. We'll come back to this later in the lecture when it becomes relevant. Our main problem for today, though, is the knapsack problem. This is exactly the Patty Larceny book stealing problem, and it comes up all over the place in computer scientific applications. How this works is our input is n objects, and each of these n objects has a weight and a value. We've also got a knapsack, and that knapsack has some upper bound on the total weight it can carry, um, some weight bound or some capacity, which we'll call big C. And the problem I want to solve is I want to find a set of objects with total weight at most C that has the greatest value possible. Maybe I've got shoes, a book, a teddy bear, and a laptop. I can only fit so many of them, and I want to fit the stuff that has the greatest value to me on, Mud's campus as I go about my day with my backpack. Um, Minor aside, this problem is a hard problem. We don't have the terminology yet to define precisely what that means, but if you know what an NP-complete problem is, this problem is NP-complete. Roughly what that means is short of an extremely surprising algorithmic breakthrough, we shouldn't expect to solve this problem in polynomial time, but we're still going to do our best. Here's an example instance. So maybe we've got shoes, book, teddy bear, and laptop. Maybe the shoes weigh 3 kilograms and have value $5. The teddy bear weighs 2 kilograms and has value $3, etc. So one reasonable way to approach this problem would be to figure out, okay, how valuable is each of these items relative to its weight? Seems like I probably would want to take the items that have a really high value for a really small weight. So I can actually pretty easily compute the ratio of value to weight for each of these items. It tells me that they have similar value density, but the laptop is the best ratio of value to weight. And as it turns out, this is a reasonable approach, and provably it will always approximate the best solution. However, it can be off by up to a factor of 2. And that results from the fact that we're using discrete weights and values. So in this particular instance, our value per weight calculation would suggest we should take the laptop. If we take the laptop, well, we've got a total weight of 7 and a value of 12. And because our weight is 7 and our capacity is 8, none of these other items will fit in the bag if we take the laptop. So in that case, we end up with a total value of 12. But in this instance, that's actually not the best solution. If I take the 3 items with slightly less value per weight, the shoes, the book, and the teddy bear, I end up with a weight of 8. So I just barely fit in my knapsack and a total value of 13. I do a little better. All that to say, this greedy approach is not a bad idea, but it won't always give you the optimal solution, so we're going to have to go a little deeper. In particular, hopefully this is not a huge surprise, we'll try a use or lose recursive approach, and we will turn this into a dynamic programming strategy. So, we remember our 5 stages of dynamic programming, analogous in my dumb joke to the 5 stages of grief. How we want to solve this problem? Well, we want to figure out some kind of recursive use or lose approach. We'll write down that approach and we'll ask ourselves, how efficient is that approach? Unfortunately, it'll turn out that that approach takes exponential time, so we'll need to do something smarter. We'll turn it into a dynamic programming approach with a dynamic programming table. So we'll need to think about the dimensions of the table, how many total calls we need, and what information we need to compute each call. We'll build this DP table, and then we'll compute the runtime based on the amount of time it takes to find our answer to fill in the table. Here's a recursive function. I've blocked out the bottom half, but to ground us in what we're doing. So the first parameter input is an array of items, and I'm going to be doing a use or lose strategy on the last item. So as I make recursive subcalls, this parameter I is going to decrease. So in particular, my first call is going to have all the items, 0 through n minus 1, and then I will gradually make decisions about the items and look at shorter and shorter prefixes of this array of items. And it's not stated here, but we'll treat each item as an object, maybe just a pair of integers. So we know the weight of each item and the value of each item, which we'll write as W of I and V of I. The second parameter is the capacity remaining in our knapsack. So that'll start as the total capacity. But as we decide to put items in our knapsack, the amount of remaining capacity will decrease. I've given you the base cases. So this first base case says, hey, if I'm totally out of items, if I'm looking at a prefix of none of the items, then the best I can do is to put nothing in my bag, return a value of 0. Also, if I'm completely out of capacity, then I also want to return 0. If I've got no capacity left, then I can't fit anything else in my bag, even if I do have items left. And if you want, now's the time you should pause the video because I'm about to show off what the rest of this function is. But I think if you want to think about it for a few minutes, you can probably work out how you might use or lose your way through this problem item by item. So our lose case, and if you want, you can pause after this case too and figure out the use case. Our lose case, if we decide that we are not going to use item number I, then we'll recurse on the array of items with one fewer item. That is, we'll throw away item I. And because we didn't actually use item I, we didn't put it in our backpack, we haven't used any of our capacity. So our capacity left over is the same as it was before. So the best we can do if we lose the item, that's our lose case. The use case, well, first we'll do a quick check and we'll say, all right, is the weight of this item bigger than our total capacity? because in that case, we kind of want to do the shortcut of we can't use this item, so we'll set the use value to 0. But on the other hand, if we pass that check and the weight of our current item is less than our total capacity remaining, we've got our use case, which says do a recursive subcall. Do that subcall with one fewer items because we have used an item. Subtract the weight from our remaining capacity. So we've put the item in the bag, so we have less capacity than we had just a moment ago. And add the value of that item to our recursive call. So we get the value of that item because we've chosen to put it in the bag. Once we evaluate these recursive calls, we're just going to return whichever is better, the result of using the item or losing the item. So that's our recursive function. And because we're making two recursive calls, and those calls might decrease both of our parameters by very small amounts, this is still potentially an exponential time. But we can build the two-dimensional dynamic programming table to solve this problem. And if you're feeling really ambitious, then you're welcome to pause the video here and solve the problem, and then you can skip the next 10 minutes of me talking. So let's do an example instance. So let's say we want to compute Knapsack on these 3 items with a remaining capacity of 6. So, sorry, these 4 items. We've got the shoes, the laptop, the teddy bear, and the book. They've got weights, and they've got values. I've changed them a little bit from the previous example, but that should be okay. And I'll also keep these 2 things on my mind. These are going to be the ways in which we fill in our table cells. And if you look back at the recursive function, these 2 things correspond exactly to what we're doing when we lose and when we use. So in particular, if we have a table indexed by the number of items and the capacity remaining, then if I want to figure out what's the best I can do with I items and j capacity remaining, the lose case will be the case in which I throw away an item and I don't lose any capacity. The use case will be one where I gain the value of the item because I'm putting it in my knapsack. I lose the item because I've processed it, and my capacity remaining goes down by the weight of the item. This is the same logic as our recursive function. So I'll fill in this cell with whichever is better of the use case and the lose case, but now I'm not making recursive calls. I'm looking at previously filled in table cells. So let's actually do this. Here's our two-dimensional table for this problem. So our table is indexed by the amount of capacity remaining from 0 to 6, 6 being our complete capacity, and by the set of items we're allowed to use. And because our recursive function is going to solve the problem from the top down by repeatedly making a use-lose decision on the last item, our dynamic programming table is going to fill in the table from the bottom up. So first off, we've got our base case. If we have no items left, think for a sec about what's the best we can do if we have any of these capacities and no items left. Yeah. This row will be all zeros because this is the case where we're not considering any items and we have whatever capacity. This column will be all zeros because no matter what items we have, if our capacity is 0, we can't put any of them in the bag. So we filled out our base cases, and all of these base cases we can fill in without making any recursive calls. Sorry, without looking at any other previously filled in table cells. Next up, we need to use our recurrence relation to actually fill in the remaining cells. So if I look at this cell first, this is the cell that asks the question, what if I have one capacity remaining and the only item I have left to consider is the shoes? So I can look at the shoes here and see, okay, the shoes have weight 2 kilograms. So in the lose case, well, I want t of I minus 1j. So in the lose case, I'll say, all right, what if I don't use the shoes? In that case, I inherit the value from the cell right above, the best I could do without the shoes. So my lose case would be a 0 for the shoes. My use case tells me, um, well, take the shoes and recurse on the cell without the shoes and with capacity minus the weight of the shoes. So I could try to take the shoes. That would tell me, look at the cell where I have capacity -1 left. And at that point, that's where my sanity check should kick in. And my table filling procedure should go, wait, I just don't have the space for the shoes in this box. So I have to take the lose call. And I end up with a 0 here. So you can see the little red arrow there. That's the lose case, and the green arrow is the use case. For the second box, though, now my lose and use calls are both valid. So again, I'm going to keep going slowly, but you can speed up if you want. If I'm trying to fill in this box, I'm asking the question, what's the best I can do if I have remaining capacity 2, and I'm just considering the item that's the shoes? And I could throw away the shoes, in which case I would look at this cell and say, all right, I get value 0 from throwing away the shoes. Or I could put the shoes in the bag, in which case I would get whatever value is left over after I use the shoes and I use up 2 of my capacity. But I would also add, and that's this term down here, I would also add the value of the shoes because I am taking them. So now my bag has 8 more value. And I can continue in this way from left to right. All of the cells in this row are going to do something similar. They're going to say, all right, in the lose case, my capacity doesn't decrease, but I also throw away the shoes. In the use case, my capacity goes down by 2, but I get the value of 8 from the shoes. Could make a very similar call for the laptop. I'm filling in this square. I'm asking if I have capacity 1, and I'm considering whether to use or lose the laptop, what's the best I can do? The lose case is just the same, but since the laptop has weight 3 kilograms, well, I can't actually use the laptop. Here I can't use the laptop. For this cell, I can use the laptop. And again, the reason why I'm now able to make the use call work is, well, if I'm in this cell, I'm saying I have remaining capacity 3. So if I use the laptop, I'll be going to a place where I use the laptop, I end up with 0 remaining capacity, and I'll be deciding on the shoes. But I'll both inherit the 0 from this cell, and I'll gain the value of 12 from using the laptop. And in fact, it'll turn out that it's always a good idea to take the laptop over losing the laptop. So for this cell, we reference this cell and add the value of the laptop. For this cell, we reference this cell and add the value of the laptop. And if you're wondering why we just went from 12 to 20, well, that's because if we have capacity, erase a couple things. If we have capacity 5 and we use the laptop, then we both get the value of the laptop, but we also recurse on remaining capacity 2 and deciding on the shoes. That is, we have enough capacity to take the shoes also. That's what that cell is telling us. So if we have capacity 5 or 6, the best we could do with the laptop and the shoes is to take them both. All right. So at this point, I'll pause and let you fill out the remainder of this dynamic programming table. Um, so if you want to do that exercise, pause now because I'm about to reveal the solutions. Oh, this is your worksheet problem, by the way, but I will assume everybody attended this virtual lecture. So the bear column is a little bit interesting because in some cases it turns out to be better to use the bear. In other cases, it turns out to be better to lose the bear. So for instance, in this particular cell, I could lose 1 kilogram and put myself in a situation where I have one remaining capacity and I'm considering the laptop and the shoes, but then I wouldn't have enough space remaining to take either one of them. So in this case, my best option is to actually lose the bear and take the laptop. But in some other cases, it's better to take the bear. The book, sadly, it turns out it's never a good idea to take the book in this scenario. It's always better to ditch the book. Last thing to ask yourself is, I filled in the table. Where is my answer? It'll be in this cell. So again, this is the cell asking the question, if I have capacity 6 and I'm deciding on all of the items in turn, what's the best I can do? And that is my original question, my knapsack problem. So that's what the DP for this problem looks like. If I want the running time, well, the running time for a dynamic program is always bounded by the size of the table multiplied by the time it takes to fill in each cell. So this table, if we have M items and C capacity, the size of the table is MC. And for every cell, I'm going to be looking at 2 other cells and doing a constant amount of work. So my total runtime is MC, which, fantastic. We've got an efficient solution to the problem. Except not quite. So let's take a closer look at this runtime of big O of M times C. This is a good runtime in a lot of cases. In particular, if we have M items, it is polynomial in M. And as long as C is not enormously big, this is a small runtime, right? If C is at most M squared, for instance, this becomes M cubed, which is polynomial in M. But if we go back to our definition, we see that a runtime like big O of M times C doesn't quite fit into our polynomial time framework because the number of bits to write down the problem input does depend on M, but it doesn't depend directly linearly on C. So in particular, what's the size of our input? Well, we have M items, and each of those M items has a weight and a value, and the size of that weight and value is at most C. So in that case, is our input size MC? Well, not quite. So what this means is that for each of the M items, we're going to write down 2 numbers. And as we mentioned before, when I write down a number with the value C, I actually am only using a number of bits proportional to log C. In other words, if C is at most 1,000,000,000, I might still only be using a small number of bits. So our actual problem size turns out to be M numbers times about log C bits. I guess 2M numbers times about log C bits to write each number down. And polynomial time with respect to our input, if we're being super nitpicky, is this value to the constant b. That is the size of our input to a constant b. So again, being super nitpicky, our runtime of big O MC is not actually polynomial with respect to the input. It's polynomial with respect to m, but if c is gigantic, the input grows like log c, but the runtime grows like the actual number c. So you can plug in yourself if we have a case where, for instance, c equals 2 to the m, which nothing about our problem rules out this case. We actually have a runtime that's exponential in m. And even though log c is factored into the input size, it still turns out that our algorithm is exponential in the size of the input. So zooming out a little bit, if that was a discussion that was hard to track, I want us to keep our eyes on this big ball, which is that usually we want to keep track of our runtime in terms of the problem input size. Here, we designed an algorithm that depended on the input size, but also on this capacity C. So if we look at our runtime of OMC, basically, we just need to proceed with a little bit of caution and say, if C is not too big, this is a great algorithm. If C is really enormously huge, this algorithm could still be pretty slow. And that's how you reconcile what we've just done with the statement earlier that we don't know how to solve this problem in truly polynomial time. We can get a good dynamic programming solution, but as long as this C is there, we're not actually, strictly speaking, in polynomial time. Now I want to switch gears and talk about a related problem called subset sum. It's actually a lot like Knapsack. In a sense, it's like Knapsack, but even a little bit simpler. So here, instead of a set of weights and values, we just get a set of numbers, which if you want, you can think of as values. And we get a target, t, and our goal is just to find a subset of those numbers that add up to exactly t. So 3 plus 10 plus 2 sums to exactly t, we're done. That's subset sum. We've got some numbers, we want to find a subset that sums to our target. So we'll solve this using dynamic programming. No, actually, we won't. We've solved a similar enough problem that it turns out we can solve this problem with an algorithm we just designed. Subset sum is similar enough to Knapsack that we don't need to reinvent the wheel and come up with a new dynamic programming algorithm. We can use the dynamic programming algorithm that we've already got. So here's the crucial realization here. And I'm going to resist my impulse to say it several times, and instead I'm going to try to say it once with the knowledge that you can pause the video and work this out. So I do think you should pause the video and work out for yourself why this is true. Here's the relationship between knapsack and subset sum. So the knapsack problem, again, this is the backpack problem, the one that we've been doing so far, gives us n items, each with a weight and a value, and a knapsack with capacity C. So we're dealing with both weights and values, and we want the best total value under a weight threshold. But as it turns out, the subset sum problem is just a special case of knapsack. So in particular, for subset sum, if we treat our n objects, our n numbers, as objects with the same weight and value, that is, if we look back at this instance, we have an item with weight 3 and value 3, an item with weight 4 and value 4, an item with weight 10 and value 10. And we set our capacity to be t, then our knapsack problem will now always try to find a solution that maximizes our capacity. Essentially, we've made it so that all of our inputs have the same weight to value ratio. How full our knapsack is always exactly proportional to how much weight we have in it. So if we can find a way to fill our knapsack to capacity T, well, that's an optimal solution to the knapsack problem. But because of the way we've set things up, if we find a way to fill our knapsack to capacity T, then we've also solved the subset sum problem. We can use our knapsack solver to get the answer to the subset sum problem just by, if we want to solve a subset sum instance, doing this little conversion and using our existing knapsack algorithm. And this is a general case of a reduction between algorithm problems. I think you've seen reductions before in CS81. So here's how we're going to think about reductions in algorithms. So I want to start by saying reductions are actually a familiar concept that you're using all the time in computer science, even if you're not a theoretician. Whenever you write a function and then call that function a whole lot of times, you're implementing a reduction. You're saying, I don't want to do this work over and over and over again. I wrote a function to do something useful, and my new problem can be written in terms of lots of calls to that problem I already solved. So I want you to imagine, for instance, that we've written down our algorithm for the knapsack solver as a piece of code, and it solves the knapsack problem, which means it's like a function where we can pass in a bunch of items with weights and values and capacities, and it'll give us the optimal knapsack solution. The way we specify the reduction is just specifying how we can use this knapsack solver to solve subset sum. So we are going to have to change our subset sum instance a little bit because our subset sum instance looks like a set of numbers and a target, but our knapsack solver, well, it wants weights and values and capacity. So our reduction, what it will do is turn our subset sum instance into an equivalent knapsack instance. That is, if we have this set of weights, we'll copy it twice to create the set of weights and values. If we have a target T, we'll set the capacity to 15. Now we have a knapsack instance, so we can pass that to our knapsack solver and get a knapsack solution. So in this case, our knapsack solution, our solver will say something like, use the items with weights 3, 10, and 2 to solve this knapsack instance optimally and get value 15 with capacity only 15. In this case, it's pretty straightforward to turn that back into a subset sum solution. But sometimes this last step can also be a little bit non-trivial. So certainly I have to explain, if I'm setting up a reduction, how to turn a subset sum instance into a knapsack instance so that solving it with my knapsack solver will get me a relevant answer. I've also got to explain how, when my solver gives me a knapsack solution, I can interpret that as a subset sum solution. So, big picture, to specify a reduction, I take some existing algorithm and I say, here's how I will take any instance of this one problem, turn it into an instance of the other problem, and here's how I will interpret the solution to the other problem as a solution to my original problem. And my proof will effectively be a proof that that procedure is valid. So to summarize it and maybe abstract it a little bit, if we want to use a subroutine for problem Y, like knapsack, to efficiently solve problem X, like subset sum, first, got to make my direction clear. So I'm reducing the problem subset sum to the problem of solving knapsack. That's like saying, if I could solve knapsack, or because I can solve knapsack, I can solve subset sum. Explain how to convert a subset sum instance to a knapsack instance. You should be able to do this for an arbitrary instance. Explain how to convert a knapsack solution back into a solution for subset sum. And finally, explain why this procedure will work and give us a correct answer to subset sum, assuming the knapsack solver is correct. One nice thing about the process of reduction is that we'll assume that we've already solved this problem. We don't have to reinvent the wheel. We don't have to reprove that the knapsack solver works. All we have to do is say something like, if the knapsack solver works as intended, this is why our reduction will let us solve subset sum. The running time of our reduction is just going to be the running time of all these three parts put together. So the running time to build the knapsack instance, plus the time to solve the knapsack instance, which will depend on our knapsack algorithm, plus the time to convert back to subset sum at the end, which is usually pretty fast. So just the time to do this process. Um, and in case you want a more detailed write-up of this, handout 3.5, which is on the canvas, goes through this process in detail and explains how I would write something like this up for a proof on the homework. So there'll be an easy reduction on the next homework. As a final note, this is the easy reduction you're going to see on the next homework. And I would suggest, since this is fresh in your brain, solve this problem right now. How would you reduce interval scheduling, that is, the class problem where we want the largest number of disjoint intervals, to weighted interval scheduling, that is, the music festival problem where the intervals have different weights? So what this reduction is going to look like is you're going to have to show how to take an IS instance, how to turn that into a solution for weighted interval scheduling. Then you'll use the algorithm that we have for weighted interval scheduling to solve to get the weighted interval scheduling solution and turn that back into an interval scheduling solution. We've already solved both of these problems. The new thing here is just, if I had some code that solved weighted interval scheduling already, how would I use it to solve interval scheduling? I have full faith in you that you can work this out and also write up a neat proof of it. And as far as reductions go, we'll go from here. So that's it for this lecture, and I will see you in class next Monday.